Okay, we're taking a look at practice exercise 2.5, and it says what truth table is implemented by the logic diagram in this figure up here. So this one right here, and here, x and y, 0, 0, 0, 1, 1, 0, and 1, 1. Now, looks like we'll need some inverts, so not x, not y. So not x just flips those, so that becomes 1, 1, 0, 0. Not y just flips these, so that becomes 1, 0, 1, 0. Now here we got this AND gate coming in here, and it's specifically x and y prime. And so this is x and not y. And remember, we think of the AND as multiplication, so multiply like normal. So we multiply the x column by the y prime column. 0 times 1 is 0. 0 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. Then this down here is bringing in not x, and it's bringing in y, or x prime y. So again, that's not x and y, and we choose multiplication. So we'll multiply this not x column by the y column. So 1 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. And 0 times 1 is 0. Then at that point, we got this right here. And again, they're kind of covering something before they really talk about it in the book. Here's our exclusive OR. We'll do the flip me. Okay, exclusive OR. If you look at the connection here, 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 0. The connection there is if exactly one of them is a 1, it's a 1. So it's real simple. When you do an exclusive OR, if one of them is a 1, it's a 1. Otherwise, it's 0. So coming over here, I'm going to look at this column. Now look at this column. If exactly one of them is a 1, then it's 1. Otherwise, it's 0. So that'd be 0. Now here, exactly one of them is a 1, so that's a 1. Here, exactly one of them is a 1, so that's a 1. And here, that's a 0. And let's go back to where we were. By the way, if they do throw something else in there like you haven't seen before, if you come and look at these right here, you can see the pattern when you look at your truth table. Like NOR, we haven't talked about yet. 0 and 0 is 1, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 0. This is taking the results of an OR and negating them, doing the invert. So like 0 plus 0 for normal OR is addition. 0 plus 0 is 0. Negating that will give you 1. 0 plus 1 is 1. Take a negation of it, 0. 1 plus 0 is 1. Take a negation of it, 0. 1 plus 1 is 2. Remember, 1 plus 1 is 1, and then negation of 1 is 0. So, NAND is a negation of the AND. So you multiply like normal and flip it to the opposite. 0 times 0 is 0, and the opposite of it is 1. 0 times 1 is 0, opposite of that is 1. 1 times 0 is 0, opposite of that is 1. 1 times 1 is 1, opposite of that is 0. Yeah, we'll talk more about that. Oh, I'm down there. Never mind. I guess I was just getting patient. Okay, so this one, we want to find a complement to this Boolean function. So f is equal to a prime b c prime. I know I put that there. A prime b c prime plus a prime b prime c. Okay, so the negation of that, or complement, we have our a prime b c prime plus a prime b prime c, and then the complement of that. Okay, so up here, these two summarize them. If you have things added together and you're doing a prime on it, then you take the prime of each one and change it to multiplication. Now in here, we have something times something else, and then we're taking the prime of it. So from that rule right here, addition becomes multiplication. You just take prime of each one. So we're going to have a prime b c prime prime a prime b prime c prime. Then, if you got multiple things inside with multiplication or ands, and you take in prime, you can rewrite it with addition, putting prime on each one. So this becomes a prime prime, b prime, except I need addition between them. Let's try that again. Plus b prime plus c prime prime. Okay, so we just rewrote that way. And then this one, that would be a prime prime plus b prime prime plus c prime. From theorem 3, involution, when you take a prime, it just the primes disappear and just gives you x. So this becomes a, and that makes sense really. You start with a, if you have a is equal to 1, you take the inverted, take the complement of it. 1 becomes 0, and then 0 becomes 1 again. So it's back where it started. Plus b prime, and then that's plus c. This one is a plus b plus c prime. Let's see if they take that and simplify it any further. Sometimes it's hard to figure out where they stop at. Okay, a plus bc plus b prime c prime. Well, one thing I do notice is that we got two things multiplied together, and the first part's the same in both of them. I don't know if that'll help us or not, but here's a and here's a. So let's come over here. We're looking for two things multiplied together. This would work because I got x plus y times x plus z. So the first item is the same. Now you might say, well, yeah, that's not the same. This is 3 items. But we consider this as 1, and we consider this as 1. We consider this as 1, and we consider this as 1. So there's actually 2 items there. So from that that property, that says that since they both start with x, the x comes first. This one both starts with a, so a comes first. And then I got a plus. And then I take the y times the z. And then again, I'm looking at postulate 4b. So I'm going to take this times this. So b prime plus c times b plus c prime. And although I've never discovered it in the properties, it's there somewhere, I'm sure. You can FOIL this. So b prime times b. So I got b prime b. B prime times c prime. C times b, or bc if I put an out order, because it is commutative. You can flip them. And c times c prime. Now, if you got b prime times b, that's postulate 5b, says that x times x prime is 0. So this would become 0. B prime c prime plus bc plus, now becomes 0. Which gives us a plus b prime c prime plus bc. Assuming I didn't make a mistake somewhere. BC plus B prime C prime. Okay, so that's how they got that answer. Grab a drink here. Now we got section 2.6, canonical and standard forms. It says a binary variable may either appear in normal form, x, or its complement form, x prime. Now consider two binary variables, x and y, combined with an AND operation. Since each variable may appear in either form, there are 4 possible combinations. We can have x prime, y prime, x prime, y, x, y prime, and x, y. Each of these 4 AND terms is called a min term, or a standard product. In a similar manner, n variables can be combined to form 2 to the n min terms. The 2 to the n different min terms may be determined by a method similar to the one shown in table 2.3, which we'll look at in a minute, for 3 variables. Binary numbers from 0 to 2 to the n minus 1 are listed under the n variables. Each min term is obtained from an AND term of the n variables, with each variable being primed if the corresponding bit of the binary number is 0 and unprimed if 1. Symbol for each min term is also shown in the table and is of the form m sub j, where the j subscript denotes the decimal equivalent of the binary number of the midterm designated. Okay, so for this right here, and this just lists all of our possibilities. So that's just brute force listing everything for X, Y, and Z. Now, in this talking about midterms right here, see how these are all zeros? That's why I got X prime, Y prime, Z prime. The prime is zeros. This one is 0, 0, 1. That's why X and Y both have primes on them, but Z doesn't, because Z is a 1. So this helps you to figure out the notation for the midterm. Does that make sense? Okay. And if I went with my, I won't finish it, but if I had 4 variables, X, Y, Z, and W. If I had 0, 0, 0, 0, then our first column here, this midterm, remember zeros are where you prime it. So this would be X prime, Y prime, Z prime, and W prime. If I had something that looks like that, I'd have X, Y prime, Z, W prime. So nothing too hard on in terms of that notation. Now the midterms were represented by little m. So m sub 0, m1, m2, m3, so forth. Now when you go to the max terms, you notice here we got X prime, Y prime, and Z prime. And these are both X, Y, Z. The primes switch to the opposite. And the multiplication became addition. Here we had X prime and Y prime, and that became X and Y. And then we had Z, which became Z prime. So it flips to the opposite, and then the operation in there goes to addition for the max terms. And these are represented by big M's. Probably the hardest part for me on this is keeping in mind the order. And there is a way to do it. Oh, I see it. I'll forget it next time I teach this class. But for this notation here, what you do is you look at this as a binary number. 0, 0, 0. Well, that's 0. 0, 0, 1. This spot here is 2 to the 0, which is 1. 1 times 1 is 1. If I went down to here, where I have a 1 here, and 0, do that over here. That corresponds to this one right here that I say is M6. Well, if I consider this a binary number, that's 2 to the 0, 2 to the first, 2 squared. And remember, you multiply these. So 2 squared is 4, 1 times 4 is 4. 2 to the first is 2, times 1 is 2. 2 to the 0 is 1, times 0 is 0, which gives us 6. And that's why it's M sub 6. Let's look at this one. This example right here. If I'm trying to see what the midterm notation is on this, this is 2 to the 0, 2 to the first, 2 squared, 2 to the third. And you got a times in between each one of those. 2 to the third is 8, so 1 times 8 is 8. 2 squared is 4, 0 times 4 is 0. 2 to the first is 2, times 1 is 2. 2 to the 0 is 1, 0 times 1 is 0. So that'd give us 10. So this notation here for our midterm would be M sub 10. Does that make sense on a notation? Okay. Now I'm going to, just in case I need this table, I don't remember, in problems, I'm going to copy this and make it a little bit easier so I don't have to keep flipping back in that ebook. And paste in the image. There we go. Okay, in similar fashion, in variables forming an or term. Okay, term similarly. Okay, nothing exciting there. Each max term is a complement of its corresponding min term, and vice versa. Boolean function can be expressed algebraically from a given truth table by forming a min term for each combination of variables that produces a 1 in the function, and then taking the or of all those terms. Okay, so it can be expressed algebraically from a given truth table by forming a min term for each combination of variables that produces a 1 in the function, and then taking the or of all those terms. So for here, we got a 1, and this is 0, 0, 1, which would be x prime, y prime, z, x prime, y prime, z. We have a 1 down here, and this would be x, y prime, z prime. So x, y prime, z prime. And next one's a 1 here. These are all 1s, so I'd have x, y, z, which is where I get the x, y, z there from. And again, this little m plus m1 plus m4 plus m7 corresponds to these. Or you can look at it and see it. So, here's the 1s. You think 0, 0, 1. What does that represent in terms of a binary number? That's 2. This is 1 times 2 to the 0. So 1 times 1, so it gives me 1. So that's why the m1's there. The 4. So where's the next one? Down here. This is 2 squared, 2 to the first, 2 to the 0. 1 times 2 squared is 4, so that's where the m4 comes from. And then this last one, this one here. This is 2 squared, 2 to the first, 2 to the 0. So that's 4 plus 2 plus 1, which gives us the 7. If I had like x prime, y, z prime, and there's an or, so it's a plus, x, y, z prime plus x prime, y, z. Now again, the primes represent their zeros. Where this one was a 0 and that became a prime. So going backwards, this is a prime, represents a 0. So this is saying that this is 0, 1, 0. This is saying that this is 1, 1, 0. This is saying that this is 0, 1, 1. Well, if I think again of this as like 2 squared, 2 to the first, 2 to the 0, this number right here is 2. So this would be little m sub 2. This one, again, 2 squared, 2 to the first, 2 to the 0. This is 4 plus 1, which is 5. So that'd be m sub 5. Can't add. Thanks. That's bad. I should have wrote 4, 2, 1 down here. I could probably do it then. Okay, so this is 2 plus 1, 3. Okay, so that's m sub 3. So that's how you do that notation if you're given these right here. Now let's take a look at function 2 before I scroll down, and we'll write that down. Okay, so we're looking for everything with a 1. Let's see. There's a 1. So we got 0, 1, 1. This is x prime, y, z. And here's a 1. So that's 1, 0, 1. That's x, y prime, z. X, y prime z. And this one is 1, 0, so that's x, y, z prime. And this one's a 1. These are all 1, so that's x, y, z. I think there's just 4 1s, right? Yeah, 4. Okay, so if I think of what this represents in terms of min terms, again, the primes are zeros. So this says 0, 1, 1. This one says 1, 0, 1, 1, 1, 0, 1, 1, 1. These are the powers of 2, just to make myself a little easier. Okay, so 1 times 2 is 2, 1 times 1 is 1, 2 plus 1 is 3, so that's m sub 3. 1 times 4 is 4, 1 times 1 is 1, so that's 5, m sub 5. 1 times 4 is 4, 1 times 2 is 2, so that's 6. And this one's 7. I should have probably read the problem closer, but I assume that this was another function of the or and so forth. M3, M5, M6, and M7. So 3, 5, 6, 7. And that's how they get that. Does that make sense so far? Okay. Okay. These examples demonstrate an important property of Boolean algebra. Any Boolean function can be expressed as a sum of min terms, with the sum meaning the ORing of the terms. We're going to see that there's something similar with the max terms. Okay. And I consider the complement of the Boolean function to be read from the truth table by forming a min term for each combination produces a 0 in a function, and then ORing those. So the complement of F1 is read as I think I got my book here. Let me look at my book. Okay, they got it correct in the book. There's an error there in the ebook. Let's see if I'm looking in the right place. Yeah, I'm looking in the right place. That's what confused me. When they say the complement of F1, there should be a prime on this F1. This is not F1. F1 is equal to this right up here. Does that make sense? Okay. If you got an ebook, then that's an error there. If you got the regular book, then it's correct in the regular book. Okay. Now, if you go backwards, if you take the complement of F1, F1 prime, then we obtain the function F1. So they kind of undo each other. F1 prime, that's from this, x prime, y prime, z prime, plus x prime, y, z prime, plus x prime, y, z, plus x, y prime, z, x, y, z prime, something missing. It should be 5. 1, 2, 3, 4. Okay. X prime, y prime, z prime. I think I have a book right here. What am I doing? Myself work harder. I need to. Okay. X. There it is. X prime y prime z prime plus x prime y z prime plus x prime y z plus x y prime z plus x y z prime. Now going in reverse, when we take complement of it, notice that each one of these, x prime, y prime, z prime, flips x, y, z. The multiplication in here becomes addition on each one of these. And then the plus, the or that's in between each one of those, becomes our multiplication or our and. So like this, these pluses here become the multiplication. So this is going to become multiplication. This is taking the complement of that, which is also the same as just F1. And then what's inside here goes from the and or multiplication to a plus or. So this would be x plus y plus z. And then this would be x plus y prime plus z. This would become x plus y prime plus z prime. This one becomes x prime plus y plus z prime. And then this one becomes x prime plus y prime plus z. Assuming I haven't screwed any of those up. Look in the book, compare it. X plus y plus z, x plus y prime plus z, x plus y prime plus z prime, x prime plus y plus z prime, x prime plus y prime plus z. Now, if we come to our max terms here, x plus y plus z. X plus y plus z. This tells m sub 0. Now, m sub 0. You have to think of it a little bit differently in this regard, because before we were interested in the reverse, right? So here, when we're trying to view this, like x plus y prime plus z, x plus y prime plus z is m sub 2. So what do you think gets the ones here if I think of it in terms of the binary? The primes. So like this would be the number 0, 0, 0, which is m sub 0, big M sub 0. This would be 0, 1, 0, and this is 2 to the first, so that's m sub 2. This one is 0, 1, 1, which is m sub. Oh, yeah. See, this is think of it in reverse in terms of that. I mean, there's nothing wrong with looking at the table and seeing that. But that's how I think of it anyway. So I think of this as 1, 0, 1. That's 2 to the fourth. That's 4 plus 1, 5. And 1, 1, 0. So 4 plus 2, 6. So m sub 6. And let me double check my book, see if I did that math right. M0, M2, M3, M5, and M6. Okay. that good so far? Okay. And then we could do the same thing with read an expression for F2 from the table. Again, you think of anything with a prime as a 1. So that's 0, 0, 0, which is m sub 0. This would be 0, 0, 1, which would be m1. This would be 0, 1, 0. And again, this would be like the 2 to the first power. So 1 times 2 to the first power is 2. So that's where the m2 comes from. This would be 1, 0, 0. And this is 2 squared. 1 times 2 squared is 4 plus 0, 0. It gives us 4. And here's the second property, Boolean algebra. Any Boolean function can be expressed as a product of max terms, with the product meaning the anding of the terms. And then procedure for obtaining the product of max terms directly from truth tables as follows. Form a max term for each combination of the variables that produces a zero-ended function. And then form the and of those max terms. So like remember what we said F1 was. So it was this. And if I come up here, so I look in the right column. Here's 0, 0, 0, 0, 0. So we're looking where everything's a 0. So we got 5 of them. Now, this first one here, if I come over here again, if I think of these, it's 2 to the powers. That's a 0, 0, 0. That's where the m sub 0 comes from. The next one, this is 0 right here. We come over here. This is 2 to the first, so that's a m2, and so forth. So you can just look at the table and build the max terms, so the product of them, or the sum of the min terms, depending upon what you're studying. Let's see, where am I at? Boolean functions expressed as a sum of min terms or product of max terms are said to be in canonical form. So if you see any problems referring to you to put it in the canonical form, that's what they're talking about. The sum of the min terms. This is a little bit strange on how it appears. And they sum it up here. Previously say that for n binary variables, one can obtain 2 to the n distinct min terms that any Boolean function could be expressed as a sum of min terms. The min terms whose sum define the Boolean function are given those that give the ones of the function in truth table. Since the function can be either 1 or 0 for each min term, since there are 2 to the n min terms, one can calculate that all functions can be formed with n variables said to be 2 to the n power. It is sometimes convenient to express a Boolean function in its sum of min terms form. If the function is not in this form, it can be made so by first expanding expression into a sum of and terms. Each term is then inspected to see if it contains all the variables. If it misses one or more, it is anded with expressions such as x plus x prime, where x is one of the missing variables. Okay, so let's look at this right here. See what in the world that wording means. We got f is equal to a plus b prime c. So we got two terms there. What we want is we want all of them to have a, b's, and c's. So when it's all said and done, this should be some kind of a, b's, and c's. This should be some kind of a, b's, and c's. Now in the process of doing that, we may have it look quite different. Now you notice in the a here, they put a b plus b prime on there. The reason why they can do that, like they say, this is A times B plus B prime. I'm writing too big. I'm not having a space. They can do that because this is multiplication, or and. X plus x prime gives you 1, which means we just simply put a 1 here. Well, A times 1 is A, so we haven't changed it all, have we? So now, I'll go ahead. Does that make sense? Okay, so we needed a b there, so we introduce a b by doing this. So if I multiply this through, A times b is AB, A times B prime is AB prime. Now over here, what letter's missing here? On the second part. Well, it has a C. It's got a B and C. It's missing an A, isn't it? So we can do the same trick. To introduce an A into this term, we can do an A plus A prime, because that's equal to 1. So then if I use the distributive property again, B prime C times A gives us A B prime C. B prime C times A prime gives us A prime B prime C. Now these are perfect because they both of these have A, B's, and C's, don't they? Now going back to here, this first term here, AB, it's missing something, isn't it? It's missing the C. Oh, okay. Yeah, sometimes I'm not very clear on which one I'm pointing to or referring to. So again, to introduce the C here, you put C plus C prime. This one is also missing the C. So I put C plus C prime. These last two are fine, so I'll leave them alone. So then distributive property, AB times C is ABC. AB times C prime is ABC prime. AB prime C AB prime times C is AB prime C. And AB prime times C prime is AB prime C prime. Let's carry down. Okay. Now we look for any duplicates. Like notice this one here, AB prime C and AB prime C. They're the same. I think that's it. Now, when you got two things added together and they're the same, theorem 1a says x plus x gives us x. So one of them will drop away. So this becomes ABC plus ABC prime plus AB prime C plus AB prime C prime, and that drops away, plus A prime B prime C. So again, duplicates, you just drop one of them. Now, we had our table here. This one is ABC. You can think of it X, Y, Z. So if I come down here and I'm looking for the X, Y, Z, that's this one down here, and that's M sub 7. A, B, C prime, if I put it in terms of X, Y, and Z, that's X, Y, Z prime. X, Y, Z prime is right here, that's M sub 6. Now, going back to our original idea, when you're talking about min terms. If it's a prime, it's 0. If it's not a prime, it's a 1. So that's 1, 1, 1. 4 plus 2 plus 1 is 7. That's 1, 1, 0. 4 plus 2 is 6, plus 0 is 6. 1, 0, 1. That's 4 plus 1 is 5. On this one, we got 1, 0, 0. That would be 4. This would be 0, 0, 1. This is 2 to 0, which is 1. 1 times 1 is 1. So give us that. Now let me check it. 7, 6, 5, 4, 1. 7, 6, 5, 4, 1. And it checks. That's what they're referring to, is that you can put it into the sum of the min terms. Does that problem make sense? Okay. Now they got a different notation for that. Instead of writing it all out this way, you put this is uppercase sigma, and then you put the 1, 4, 5, 6, 7 off of that. So that's kind of a shortened way to write it. Brief notation. Let's do one more. So let me clear that off. You don't save. Okay, so I got AB plus C prime plus A. Now the three variables I have are C. Now you don't introduce a variable you don't have. So you don't put like D and E and F in there. So this first one here is missing a C. So I'll put C plus C prime. To begin with, this second piece right here is missing an A. I could, while I'm doing this, go ahead and put the B plus B prime here too, because it's missing both A and B. This one is missing a B, so I have B plus B prime. This one's also missing a C, so I can put C plus C prime. And then it kind of goes back to your algebra. Foiling, or not, you don't have to foil here, but yeah, I do. Never mind. AB times C is ABC. AB times C prime is ABC prime. I could do it two different ways. I could foil this first, or I could multiply these together. It doesn't matter. If I multiply these together, C prime times A is AC prime. C prime times A prime is A prime C prime. And that carries down. Here, A times B is AB. A times B prime is AB prime. C plus C prime. So I got ABC plus ABC prime. Foil this. So I take AC prime times B, that gives me ABC prime. AC prime times B prime is AB prime C prime. A prime C prime times B is A prime B C prime. A prime C prime times B prime is all of them primed. AB times C is ABC. AB times C prime is ABC prime. AB prime times C is AB prime C. And AB prime times C prime is AB prime C prime. B C prime, all primed. AB times C is ABC. AB times C prime, that. AB prime times C. AB prime times C. B prime, C prime. Okay. Now I'm going to look for duplicates. Well, I got an ABC here, and I also got an ABC here. So one of them disappears. ABC prime. That's weird. Those are the same. Huh. ABC prime. There's another ABC prime. So those become one. Again, if you got duplicates, triplicates, whatever, they just reduce down to one. Here's A, B prime, C prime. A, B prime, C prime. I see an A, B prime, C prime down here. So that goes down to one of them. See any duplicates of that one? See any duplicates of that one? And that's the last one. Okay, now ABC. Again, I could use my table. ABC, different letter, but same idea. That tells me it's M sub 7. Again, you could use a table, or if you want to put ones in like that and zeros for primes. Okay, this would be 4 plus 2 is 6. So that's M sub 6. This one's 4. This one's 2. That's 1, 0. This one's 4 plus 1 is 5. Assuming my eyes didn't get off. Now, their brief notation they have here, you put your sum, and then you, with parentheses around it, you put your subscripts. So smallest one is 0, 2, 4, 5, 6, and 7. And that'd be our answer. Questions on that one? Okay. Just kind of tedious algebra there. Making sure you get all the primes down. You can see how it helps you to know the binary number system, because you run across it so much. The alternative procedure for deriving the minterms of a Boolean function is to obtain a truth table of the function directly from the algebraic expression, and then read the minterms from the truth table. So they're back to this. F is equal to A plus B prime C. Got the truth table down here for it. We derive directly from the algebraic expression by listing the 8 binary combinations under variables A, B, and C, and inserting ones under F for those combinations for which A equals 1 or BC is equal to 0, 1. From the truth table, we can read the 5 minterms of the function to be 1, 4, 5, 6, and 7. Okay, I see why they're saying that. Because remember, if you got A and you got, why did they say BC there? This is, where am I at? They got a little problem there. Do you see what the problem is? Up here they say B prime C, don't they? But down here, what do they use? BC. Now you may wonder, we want an F for those combinations, which gives you one here or one here. Well, that's because one plus zero is one, zero plus one is one plus one is one. So all those will give you this. But they should have said right here, B prime C. Does that make sense? Oh, yeah, they got an error there. I think next time we'll start off here, and I'll build a truth table based upon what it should be, just to see if the truth table is correct or not. But we'll go ahead and stop there. And we've got far enough into the chapter now. I'll put some homework out because I wanted us to get used to working with these properties, and you've seen these properties over and over now. So hopefully, the problems in homework become pretty easy.